Welcome to today's paper reading. Today's paper is titled Kolmogorov, Arnold Transformer. This paper was published on AR14 by Xingyi Yang and Xinchao Wang from the National University of Singapore. The Kolmogorov, Arnold Transformer, KT, is a novel architecture that replaces traditional multilayer perceptron, MLP, layers with Kolmogorov-Arnold network, KN, layers. This change aims to enhance the expressiveness and performance of the model. However, integrating KNs into transformers presents several challenges. First, the base function, typically a B-spline, is not optimized for parallel computing, leading to slower inference speeds. Second, KNs require unique functions for each input-output pair, resulting in significant computational load. Third, the initialization of weights in KNs is complex due to their learnable activation functions. To address these issues, we propose three solutions. We replace B-spline functions with rational functions to improve GPU compatibility and speed up computations. We introduce group KN to share activation weights among neurons, reducing computational load without compromising performance. Finally, we implement variance-preserving initialization to ensure stable activation variance across layers. These innovations enable KT to scale effectively and outperform traditional MLP-based transformers across various tasks. Figure 1 illustrates the architectural differences among standard transformers like VIT, VIT plus KN, and our proposed KT model. On the left, it shows how KT substitutes the traditional MLP layers with GRKN layers, enhancing the model's expressiveness and performance. The right side of the figure presents the performance metrics on the ImageNet dataset. Notably, KT*, which uses pre-trained VIT weights, generally outperforms both VIT and DT models. In contrast, VIT plus KN, despite its architectural modifications, faces significant challenges during ImageNet scale training, resulting in poor performance. This highlights the scalability and efficiency advantages of KT over other transformer variants. Transformers have become the standard architecture in deep learning, particularly in computer vision and natural language processing. At their core, they rely on attention modules and multilayer perceptrons, MLPs. Despite their widespread use, MLPs face limitations in modeling complex functions, such as difficulty with periodic functions and prolonged convergence times. Kolmogorov-Arnold networks, KNs, have emerged as a promising alternative due to their theoretical parameter efficiency and suitability for symbolic regression tasks. However, integrating KNs into transformers has faced challenges, including base function inefficiency, parameter and computational overhead, and weight initialization issues. This paper introduces innovations to address these challenges, aiming to enhance the performance and scalability of KN-based transformers. The preliminary section introduces the Kolmogorov-Arnold representation theorem, which states that any multivariate continuous function can be expressed as a finite composition of continuous univariate functions. This theorem is foundational for the development of Kolmogorov-Arnold networks, KN, which generalize this concept into neural network layers. However, the original KN faces challenges in scaling, prompting the use of parameterization with CLU activation and B-spline functions to address these issues. The original KN model faces significant scalability issues due to several design choices. Firstly, the use of B-spline functions, which are not natively supported in CUDA, leads to slower performance on GPUs and inefficient parallel processing. Secondly, KN's design inherently increases the parameter count and computational demands, making it less efficient compared to standard neural networks. Lastly, the initialization strategy in KN deviates from the variance-preserving principle, leading to potential instability in model training. The Kolmogorov-Arnold transformer, KT, is designed to replace the multilayer perceptrons, MLPs, in vision transformers with Kolmogorov-Arnold network, KN, layers. This involves flattening a 2D image into a 1D sequence, applying patch embedding and positional encoding, and then passing it through a series of KT layers. At each layer, operations include multi-head self-attention, MSA, followed by layer normalization, LN, and the addition of the previous layer's output. The key enhancement in KET is the replacement of MLPs with KNs, which involves using rational base functions and implementing a group rational KN to share parameters among a group of edges. Additionally, a variance-preserving initialization scheme is introduced to ensure stable training. Figure 2 provides a comparison of our group KN with vanilla KN and multilayer perceptrons, MLPs. The key distinction lies in the function assignment and parameter sharing. While KN assigns a unique function to each input-output pair, group KN implements parameter sharing among a group of edges, thereby reducing the number of parameters. In contrast, MLPs utilize non-learnable activations, which sets them apart from both KN and group KN. This figure highlights the architectural differences and the computational efficiencies achieved through group-wise parameter sharing in group KN. Figure 3 presents an example of fitted functions using a rational form. The rational function is defined as a0 plus a1x plus mxm / 1 plus b1x plus bnxn. These functions are fitted to common activation functions such as ReLU, GELU, and Swish. The gain alpha, calculated as var x/EF x superscript 2, is a key parameter in maintaining consistent activation scaling. This figure illustrates how rational functions can be tailored to mimic the behavior of established activation functions, providing a visual reference for the fitting process. Figure 4 illustrates the one-to-one weight mapping strategy between the trained multilayer perceptron, MLP, envision transformer, VIT, and the group-wise rational KN, GRKN, layer in the KET model. The GRKN layer is composed of a linear layer and a group-wise rational layer. This structure allows for the direct transfer of weights from the linear layer of the MLP in the pre-trained VIT to the GRKN layer in KET. For the rational layers within GRKN, the first layer is initialized to function as an identity, while the second layer is configured to approximate the nonlinear function used in the original MLP. This method ensures that all weights in the GRKN layer can be cloned from the VIT model, facilitating compatibility and efficient initialization of the KET model. Table 1 provides a detailed comparison of the floating point operations, flops, required for different functions. The B-spline function with parameters g equals 3 and k equals 3 requires 204 flops. In contrast, the rational function with parameters m equals 5 and n equals 4 requires 46 flops. When the rational function is evaluated using Horner's method, the flops are further reduced to 21. This significant reduction, approximately 9.3 times less than the B-spline function, highlights the computational efficiency of the rational function when optimized with Horner's method. Table 2 provides a detailed comparison of the parameter counts among different models, specifically focusing on the number of parameters and computational efficiency. The table highlights that our GRKN model maintains a parameter size that is only a constant increase over the standard MLP, while the KN model's parameters scale with the sum of grid number, order number, and an additional constant factor of 3. This scaling difference is significant as it demonstrates the efficiency of our grouping strategy in GRKN, which not only reduces the number of unique activation functions required but also significantly lowers the computational demands by allowing the sharing of activation functions across input channels. This efficiency is crucial for practical applications where computational resources are limited. Table 3 presents the expected values of x2 for various functions, which are crucial for the initialization of weights in the group rational KN, GRKN, layer. These expected values directly influence the variance-preserving initialization process, ensuring consistent activation scaling across layers. The gain alpha, calculated numerically, is used to initialize from a normal distribution, maintaining the stability of the network. This table is essential for understanding how different functions affect the initialization of weights in the GRKN layer, contributing to the overall stability and performance of the network. The experimental setup involves modifying the vision transformer, VIT, architecture by replacing its MLP layers with GRKN layers. These KN layers use a rational function with specific parameters and are organized into groups. For image recognition tasks, experiments were conducted on the ImageNet 1K dataset with extensive data augmentation techniques. In object detection, the KT model was used as the backbone in a VITDET-based mask-RCNN model, trained on the MS COCO 2017 dataset. These setups were chosen to evaluate the performance and scalability of the KT model in various computer vision tasks. Table 4 provides a detailed configuration of the KT model variants, which include KT Tiny, KT Small, and KT Base. Each variant consists of 12 layers, with varying hidden sizes ranging from 192 to 768, and MLP sizes from 768 to 3072. The number of heads varies from 3 to 12, and the models have parameters ranging from 5.7 million to 86.6 million. These configurations are designed to be identical to those used in VIT, ensuring a fair comparison in performance. Table 5 presents a comparative analysis of model performance and computational efficiency on the ImageNet 1K dataset. The table highlights that the KTS model achieved an accuracy of 81.2%, outperforming the DTS model by 2.4%. This improvement demonstrates the effectiveness of KN mixers in enhancing model efficacy. Additionally, the table shows that the vanilla KN layer faces scalability issues, as evidenced by the VITL plus KN model failing to converge and resulting in an NAN error. Despite these challenges, the KT model successfully balanced computational efficiency with improved performance, suggesting valuable directions for further research in optimizing transformer architectures. Table 6 presents a comparative analysis of the performance of mask-RCNN using various backbones on a 3x training schedule. The table highlights that KT consistently outperforms other models, particularly in object detection metrics. For instance, KTDET-S achieves 48.48 box with 66.9 flops, while KTDET-B scores 51.68 box with 770 G flops. These results underscore KT's effectiveness in delivering superior accuracy with minimal computational overhead, making it a valuable addition to the field of object detection and instance segmentation. Table 7 presents the performance of semantic segmentation using UpperNet on the AD20K validation set. The images were cropped to 512 by 512 for training, and the max were measured with an input size of 512 by 2048. The table highlights that KT demonstrates a competitive improvement over plain VIT-based architectures. Specifically, KT achieves a 2.4% improvement over DTS and a 0.2% improvement over DTB. This performance boost comes with a slight increase in computational cost, reflected in the higher flops. Despite the increased computational cost, KT shows more significant gains in smaller models. However, it still falls short compared to models with hierarchical architectures, such as CONVNXT, which benefit from more efficient structural design. Table 8 presents an ablation study on various activation functions using the VITT/16 variant. The study evaluates the impact of different activation functions on the top 1 accuracy of the ImageNet 1K dataset. Activation functions tested include GELU, ReLU, CLU, PReLU, and PU. The results show that traditional activations like GELU and ReLU perform similarly, while learnable activations such as PReLU and PU demonstrate improvements. Notably, the KT model, which incorporates GRKN, achieves the highest accuracy at 74.6%, outperforming GELU by 1.9%. This suggests that GRKN significantly enhances the expressiveness of MLPs in vision transformers. Table 9 presents the throughput and peak memory usage of various activation functions on an NVIDIA A5000 GPU with a fixed input size of 64,1512. The data reveals that while traditional activations like ReLU, GELU, and CLU exhibit similar peak memory usage, their throughput differs. Notably, our method KT achieves the highest accuracy but shows a slightly lower throughput compared to the baseline activations. This indicates a trade-off between accuracy and computational efficiency, likely due to the complexity of rational function computations in KT. Table 10 presents the results of an ablation study on the initialization of rational functions within the KT model. The study evaluates different initialization strategies, with the identity swish initialization demonstrating superior performance, achieving the highest top 1 accuracy on the IN1K dataset. This initialization method has been adopted as the default setting for the KTT model. The table clearly shows the impact of different initialization techniques on the model's performance, highlighting the importance of rational function initialization in achieving optimal results. Figure 5 presents a comparison of throughput and peak memory for different methods and group sizes, with the input size fixed at 64,1512. The figure highlights the performance of various methods in terms of both processing speed, measured in batches per second, and memory usage, measured in megabytes. This comparison is crucial for evaluating the efficiency of different implementations, particularly in the context of CUDA optimizations discussed in the paper. The results indicate how each method scales with varying group sizes, providing insights into their relative efficiency and resource utilization. Figure 6 presents a detailed comparison of throughput and peak memory usage across various methods and input dimension sizes, with the group size fixed at 8. This analysis is crucial for understanding the performance characteristics of each method under consistent group size conditions. The figure highlights the differences in computational efficiency and memory management among the methods, providing insights into which approaches offer the best balance between speed and resource utilization for specific input dimensions. Figure 7 illustrates the fitted rational functions for the KTS model, which consists of 12 layers and 8 groups. The visualization reveals that within each layer, the rational functions exhibit similar trends. However, the functions across different layers tend to differ from one another, highlighting the model's complexity and adaptability. The Kolmogorov-Arnold transformer, KT, has demonstrated significant improvements over traditional MLP-based transformers, achieving superior accuracy on ImageNet 1K while maintaining comparable computational demands. However, challenges such as running speed and stability issues with rational functions remain. Future research could explore alternative base functions, expand KT's applicability to NLP and RL, and address scalability challenges to deploy KT in real-world applications. Thank you for watching.